Once again, good old answer key. How much work is done? So work equals force times distance. It starts there, and then we modified it occasionally. Mark and take-home quiz, kiddo. Here, it looks like the force and the distance are in the same direction, so it's going to be 767 times 28. No idea what that is. Do you get 21,000? I'm going to go 21,500 joules. Where has that energy gone? Because it's got to go somewhere. They've done work in joules. Where has that energy gone? When you push on a car, what happens to it? Sorry? Be really obvious. When you push on a car, what happens? Huh? And so if it's moving, what kind of energy is it gaining? This is going into kinetic energy. And because there's an unbalanced force, this will be accelerating. Now, if you push it for 28 meters, you would start out with it really slow, but it would go faster and faster. And so by the end of this, you'd probably be sprinting. There would come a point when you reach your maximum speed. And so now the force is balanced. But anyways, yeah, it's going into kinetic energy. It's causing this car to speed up. Suppose they complete this task in 58 seconds. How much power will they generate? Well, power is work over time. Kenley, I'm going to write 21,500, but I'm going to use my answer button. Do you get 370 powers measured in watts? Yes? About a half a horsepower, if my memory serves me correctly. How much work is done by a forklift? Right, what did I say? 1 mark each. Yeah, 1 mark each, so I'm going to go half mark for the equation, half mark for the answer, but if you got it right, 1 out of 1. How much work is done by forklift raising? When you're lifting, we said that work specifically turns into mgh because the force you're doing up is the same as gravity down and h, and that also stores potential energy in it, which we learned a couple of days ago. It'll be 688 times 9.8 times 2.8 meters. 1 story, basically you're lifting it up to the 2nd floor. You get 18,900 joules. How much power? You know, question 1 and question 2 are really similar, I think. We're calculating work in different ways. And again, I'm going to write 18,900. But I'm going to use my answer button. Why did I write 73 seconds? This is lifting the piano pretty slowly. To lift it 1 story but take over 60 seconds, this is a very slow-moving, meticulous motor. It's about a 259 watt motor. Work a vector or a scalar? Work is measured in what? Which, by the way, is technically a Newton meter because it's force times distance, but you don't need to write that. I'm just giving you the nerd trivia of where it came from. We call that a joule. Power is measured in what? Watts. Horsepower, if you're American, no. Okay, what's the minimum power? Power is work over time. Since we're climbing, the work is going to be mgh over time. So it's going to be 64 times 9.8 times, 82 stairs times 0.21. You know what? This is the stairway lab that we did a few days ago. It's the same physics. It's going to be 64 times 9.8 times 82 stairs times 21 centimeters each, divided by 83. Yeah, some of you almost walked that slow. Oh, yeah, I went there. 130 watts, yes? Okay. How many stairs in this question? How many seconds? They're basically doing a stair a second. You could keep that up for a while. 130 watts. I mean, after 5 minutes, you'll be feeling it probably, and you might start to sweat after 10 and breathe heavy after 15. But 1 stair a second, that's pretty step, slow, step. I don't think that's too big of an effort, just to put it into context for Logan. Same idea, it's going to be 25 times 9.8. I'm noticing some of these questions are pretty repetitive. Times 24 all over 32. This might work out evenly. 25 times 9.8 times 24 divided by 32. 184 watts. Efficiency. So efficiency had that funky symbol, although you could also abbreviate efficiency with EFF for efficiency. And that's equal to the smaller number divided by the bigger number. Well, I'll write it the way I gave you in the official definition. I said it's power out divided by power in. Here, it's a little easier to tell which one is out, which one is in. This is what we got out. I'm going to write 184, but I'm going to use my answer button. This is what we put in. And then times 100 to make it a percentage. So it's going to be this number divided by 244 times 100. This is about 75.3. I'm just going to go to 2 sig figs. 75% efficient. Which tells me this is almost certainly an electric motor, not a gasoline engine. Gasoline engines are usually around 30% efficient. They give off lots of heat. The 65 Newton force is horizontally applied to a mass of 12 kilograms sitting on a level floor. Okay. How much work did the applied force do? The work done by the applied force is going to be the force applied times distance. The force applied is 65. 65, Mr. Dueck. Why did I write a 4? Don't know. The distance is 14. 910 joules. Yes? How much work does friction do? Well, the work that friction does is going to be the force of friction times distance. Friction is what times what? It's going to be mu times the normal force times distance. Antonio, I need to do a quick free body diagram here. I think I have gravity down, normal force up. There's an applied force of 65 newtons, and there's friction. I don't know the normal force. Oh, but look. I don't know the force the same size as the normal force. I can say it's going to be mu mg times distance, and so it's going to be 0.25 times 12 times 9.8 times 14. 0.25 times 12 times 9.8 times 14. Do you get 411.6? I'll go 412. If you call this negative or positive, I'm not going to be fussy. I would argue technically it's negative work because we're losing energy. 412 joules, 411.6 joules of energy. Blake, I won't be fussy on the negative or positive there, but for part C, when it wants you to find the net work, what you're going to do is go 910 minus 411.6? Or if you made this negative, you would go plus negative. All I'm saying is you're losing energy to friction. The net amount of work, no, not divided by, minus answer button, is 498 joules. That's the energy that went into this mass, where causing it to speed up. So as you were pushing this, Kenley, making it go faster and faster, it turns out even though you gave up 910 joules of your own energy to do it, 412 joules went into heating up the floor, and only 498 joules went into causing this to speed up. But I do know the energy had to go somewhere. It can't just magically vanish. Can you give yourself a lovely score, please, out of 13? And then make sure your name is on them and pass them inwards. So what does the law of conservation of energy say? Energy can't be created or destroyed. You know what, Riley, in a nutshell, it says the energy's got to come from somewhere and go somewhere, and you can track where the energy is stored along the way. Slingshots are a great example, much like bows and arrows, of conservation of energy. So suppose a slingshot is pulled with an average force of 70 newtons for a distance of 90 centimeters. Well, first thing, 90 centimeters, nice try. How many meters? 0.9 meters. How much potential energy is stored in the slingshot? This potential energy is not mgh, Courtney, because we're not lifting it up. We're not giving it energy because of gravity. We're storing energy by doing work. Newtons, what's that a measure of? Meters, what's that a measure of? I'm thinking we're going to start out figuring out that the potential energy stored is force times distance. Now, this isn't blatantly on your green sheet, Antonio. You're going to make it because that was a mighty long blink. I'm calling you out right now. It's on. Evan, you might need to help him out a little bit because he's looking like a little zoned there. So this is stored energy by doing work, Rowan, not by going mgh, lifting it up. And so that's why you'll often hear me say gravitational potential energy when I mean mgh, and just potential energy, stored energy of all types. So it's going to be 70 times 0.9. Double check me, 63 joules, yes? I think I can do that much in my head. Is it 63? It's not? Good. So, what's more interesting then is if I put a 35-gram rock in the slingshot, I can figure out how fast it will leave. How? Well, watch for a second. Don't write this first bit down. This is a conservation of energy question. This is kinetic initial, don't write this down, plus potential initial equals kinetic final plus potential final. But I can simplify this. Before we let go, what's the only type of energy that this system possesses? Is it moving, Kenley? So I'm going to argue that all it has at the beginning is that stored energy, 63 joules. And after I let it go, how much potential energy is left over stored? You know what? You can write that down. Potential initial turns into all the final kinetic. That's a modified version of conservation of energy. And that, Riley, is anytime you're firing a gun, all of the stored chemical energy gets turned into kinetic, or if you're firing a slingshot or firing a bow and arrow, all of that stored energy from the rubber band, from the bow and arrow, from the slingshot, from the bow, gets turned into kinetic. In fact, it's going to be this. 63 equals a half mv squared. How would I get the v by itself? How would I move the m over? Divide. And then you can either divide by 0.5 or times by 2, and that's going to give me a v squared. So in my mind, and I really set this up badly, I'm going to move this way. I'm going to have v squared equals 2 times 63 divided by m. Logan, how to get rid of a squared? Got to be kidding. No, how to get rid of squared. Yes. Oh, what's the mass, folks? I should have crossed this out. I don't do physics with grams. What is it really? 0.035 kilograms. How fast will it leave? 2 times 63 divided by 0.035. Holy smokes, this does work out evenly? I must have made up some nice numbers. Normally I don't care about you guys enough to do that. Exactly, in theory, 60 meters per second. Would that work in real life, Mr. Dueck? It would be close. There would actually be some heat inside the rubber bands. If you stretch rubber back and forth, it does get warmer, so you'd lose some energy to that. And there would be the sound of the launch. That takes some energy. It's got to come from somewhere, so you wouldn't quite get 60 meters per second. You'd probably get closer to 55, 56, 58 maybe. Example 2. Tarzan weighs 82 kilograms and runs at 8 meters per second. He runs along the ground and grabs a vine, swinging into the air. What maximum height does he reach? Who remembers, what does DULP stand for? I think I've told you this. We're going to draw a little picture. So here's Tarzan. And he is running, so there's 1 foot. There's another foot. He's sprinting as fast as he can. That's about as good as you'll ever see me draw a picture. And there's a vine hanging right here. Tarzan's going to grab the vine and swing up. And we'd like to figure out how high he goes. Is that okay? Have any of you ever tried running at a rope swing, grabbing it, and just seeing how high your energy can carry you? Have any of you tried that before? I don't know if there's a good rope swing around here. There was one where I was growing up when I was a kid, but we had one at a cabin where I was growing up. My grandpa put a good one there and went out over water so you could try and take a big run and see how far you would go out and let go and land in the water. Kenley's going, oh, that would have been awesome. Yeah, you missed out. My childhood was way better than your childhood. Okay, never mind. Got the argument? Kenley, I think we're going to call this, and I think we're going to call this, yes? Antonio, after Tarzan grabs the rope, will there be a change in speed? Sorry, I can't hear you. Yeah. Will there be a change in height? Is there a yucky, curvy path? This is absolutely a job for conservation of energy. Some of the other questions that we've done where there wasn't a yucky, curvy path, I might have been able to solve them using other methods, but this one here, because energy is a scalar, it doesn't care about that curvy path. It just cares about where you started and where you ended. So let's write out the full conservation of energy G equation. Initial plus initial equals final plus final. Mr. Dueck, how come you went kinetic and then potential plus kinetic? The order doesn't matter. All I'm saying is, Jagger, it's initial plus initial. It has to equal final plus final. Are any of these 0? Let's look at the kinetic energy first. Is there ever a time where Tarzan's going to come to a stop or be at rest? I think at the very top, he's going to slow down. Whenever he reaches his max height for a split second, I think he's stopped. I think final is that. What about height? Is Tarzan ever on the ground? Where? There's a bit of a problem here, though, because that's the ground, but don't write this down. How do we take that into account? Here's the beauty of conservation of energy. You can let the ground be wherever you want it to be mathematically to make it convenient. So even though technically that's the ground, since I'm measuring the height from the bottom of the rope, Kenzie, I'm going to let that be the ground. I'm allowed to because conservation of energy is a scalar. And so I can say that, and this is going to find how high from the bottom of the vine he ends up going. That trick's going to come in handy when we look at roller coasters later on as well. If we're looking at 2 hills, we'll just let one of the hills be a height of 0. Pretend that's the ground. So I end up with a half mv initial squared equals mgh final. Sam, how many terms are there in this equation?
2.
Is there an m in the term on the left-hand side?
Yeah.
Is there an m in the term on the right-hand side?
Yeah.
Is there an m in everything? Well, then, for what it's worth, I can cancel the mass. Now, you don't have to. If you leave the mass in, you will get the same answer as all of us. But what this says is not only would Tarzan swing to this height, if Tantor the elephant ran at 8 meters per second, and assuming the vine didn't snap, Tantor the elephant would swing to the same height. That's kind of cool. What are we trying to find? How do I get the height by itself? So the final height is going to be vi squared over 2g, or you could write it as 0.5 vi squared over g. It depends whether you chose to make that a 1/2, or whether you chose to make that a 0.5. I don't care. They're the same equation. How high? 8 squared all over 2 times 9.8. 8 squared all over 2 times 9.8. You get 3.27 meters. Yeah. And kind of neat, doesn't matter what the mass is, the mass cancels. As long as you hit that rope at 8 meters per second, everyone would swing to the same height. Good stretch. You guys did you didn't see, you guys did a unison stretch right there. It was like synchronized stretching, both of you. Yeah. Slap shots are great examples of energy transformations. I'm going to show you this video, but not right now. Make sure I don't forget to show you the physics of slap shots, because I know I have some hockey players in this room, and there's some gorgeous physics there. Next page. I love roller coasters. I love example 3. I love example 3. I love example 3. Example 3 is a gorgeous question. Blake, what's part A asking me to find? Where? What location? Point B. The other thing is, if you're a ride designer, you can decide how fast you want them to be going at the bottom and figure out how high you need to build the first hill. Here, I'm telling you how high the first hill is. We'll figure out how fast we're going at the bottom. This is the one, if you take Physics 12, that you'll use to analyze the roller coaster. You'll use some basic trig to figure out the height of the first hill, and you'll be pretty accurate with how fast you're going at the bottom, because the wooden roller coaster, they grease that down pretty good. You're not losing a lot of energy to friction. It's reasonably accurate. Meanwhile, let's see. Blake, is there a change in height? Is there going to be a change in speed? Is there a yucky, curvy path? This is a job for conservation of energy. If you don't mind, Blake, I'm going to let this be initial and this be final. I'm going to write our conservation of energy equation. Initial plus initial equals final plus final. Blake, do I need to go plus heat? Do I need to include heat? What are the last 2 words of this question say after part A? Last 2 words right there. Read that out loud. Read it out loud. Ignore. So say it again. Oh, so I won't add heat. We'll pretend this is a perfect roller coaster, that we don't lose any energy to heat. Hey folks, are any of these 0? Oh. Why can I do that? Because my final height is 0, yes? And barely makes it over the first hill. I think they're trying... Oh, yeah, it says assume VI is 0 in brackets. So we can say that. And we end up with potential energy. Now, this is gravitational potential energy. We're going to end up with mgh initial equals a half mv final squared. Blake, have you gone on a roller coaster before? Before you got on the roller coaster, did they make you step on a scale? Did they have to get your mass and carefully spread everybody out? Yeah. Is there an m in this term? Yeah. Is there an m in this term? Yeah. Mass is canceled. What are we trying to find? How do I get the speed by... I got to be fussy, by the way. It's speed, not velocity. We're in Scalarville. How do I get the v by itself? You can either divide by 0.5. I'm going to times by 2 because it looks prettier. So I'm going to write 2gh initial. And if you don't mind, Blake, I'm going to put the vf squared right there. Logan, how to get rid of a squared? There. Trying to solve this by using forces, Antonio, you'd have to take into account all of the changes in angle, and you'd have to calculate a separate acceleration for each one of them. You can do it using calculus, You don't want to do a vector approach. You want to do a scalar approach that doesn't care about all those bumps in between. What'd you get, Logan? That's my way of saying time to write this out and plug and chug. Saw you waiting for me. I've scrolled down. What was the initial height? Oh, 18. Okay. 2 times 9.8 times 18. 350, square root. You get 18.8 meters per second? Is that fast? Times it by 3.6 just to find out. Not bad. It's about what the wooden coaster does at Playland, and it's pretty intense. Okay, I've been on faster, but I've been on coasters that were slower too, so that's not bad. I'd go on that. I'd go on that without thinking, oh, I'm gonna, dry my eyes out and see tunnel vision, and holy smokes, my heart rate's gonna go through the roof. I just go on it for a thrill ride because it's a good coaster. How can we get it to go faster? Give it an initial speed at the top of the first hill. So part B, supposing we had an initial speed right there, it's going to start the same way, Savannah, because there's still a change in height, there's still a change in speed, there's still a yucky curvy path, so we're still going to start out with conservation of energy, G. We're still ending up on the ground, so we can still cross out potential energy final, but I can't cross out initial. How do I calculate kinetic energy? A half m v initial squared plus potential energy m g h initial equals a half m v final squared. Riley, how many terms are there in this equation? 3. Is there an m in the first term? Is there an M in the middle term? Is there an M in the last term? Riley, have you gone on a roller coaster before? When you went on, before you got on, did they make you step on a scale? Really? Why? Really? Yeah. Hey, look up. I'm going to show you a great trick. Since there's a 1/2 there and there, I'm going to clear fractions, which I think you just recently learned or reviewed in Math 11. I'm going to go times by 2, times by 2, times by 2. Evan, did I multiply everything by 2? So have I broken any equation solving rules? Nope. Did the same thing to both sides. But what's nice is that 2 and that 1/2, that's a 1. 2 times a half. And that 2 and that 1/2, that's a 1. And you end up with this. VI squared plus 2GH initial. And if you don't mind, I'm going to put the VF squared right there. Did I already show you what equation this is in disguise? That this is actually VF squared equals VI squared plus 2AD in disguise. That's really where the equation comes from. Logan, how to get rid of a squared? So it's going to be the square root of 22 squared plus 2 times 9.8 times 18. This one's going to be going a lot faster at the bottom. This ride is going to have some kick. I get 28.9 meters per second. Is that correct? See someone else nodding? I see a couple of nods. Yeah. If you multiply that by 3.6, yeah, now we're going freeway speed. That's a good coaster. Although I've gone faster. But 104 is pretty good with no roof in an open car. That's pretty good. Turn the page. Suppose the roller coaster in part B is only traveling at 25 meters per second at the bottom. How much energy was lost to heat? Huh. Jabber, what's this question asking me to find? Not quite. Just read to me the last sentence, kiddo. The heat. So I'm going to still use conservation of energy because there's still a change in height, there's still a change in speed, still a curvy path, but I'm going to modify it. Now I'm going to say, okay, it's still going to be initial plus initial equals final plus final, but now they're saying some of the energy went into heat. Otherwise, the numbers don't balance. Now, potential energy final is still 0 because we're ending up on the ground. Kinetic energy initial, not 0 because it says part B. Jabber, how would I get the heat by itself? Yeah, you know what? You're feeling the heat now. Nothing? Okay. It's going to be kinetic initial plus potential initial, left side drops down like a domino, minus kinetic final, and if you don't mind, I'm going to put the heat by itself on that side. Heat is going to be, how do I calculate kinetic? Oh, a half mv initial squared plus mg h initial minus a half mv final squared. Jabber, how many terms are there in this equation? Do the m's cancel this time? No m in heat. So if we do allow for friction, it's true the mass doesn't cancel. But if we really grease this roller coaster down, we can make this heat really, really small, near 0. And so in real life, for all intents and purposes, the mass cancels. An empty car can make it through the roller coaster the same as a packed car. Meanwhile, let's crunch the numbers. Heat equals 0.5. What was the mass? Canceled it out every time. 255. What was VI? 22 squared plus 255 times 9.8 times, what was the height? 18 minus 0.5 times 255 times the actual speed was 25 squared, not 28.9. How much energy did we lose to heat? A half mv squared plus a mgh minus a half mv final squared. You get almost exactly 27,000, 27,004.5. So I'll go 27,000 to 3 sig figs. And it's heat, which is a form of energy, so it's going to be joules. I'm going to skip example 4. We'll come back to it and go to example 5. There's something called Rube Goldberg machines or chain reaction machines where they're good examples of energy transformations. Outside of science world, there's that ball sculpture with the rolling billiard balls that move all through that. That's a great example of a Rube Goldberg or energy transfer machine. They're named after a cartoonist named Rube Goldberg who used to draw them on the back cover of I think it was the Saturday Evening Post, these elaborate contraptions to perform simple tasks. I love Rube Goldberg machines. Spot the energy transformations in this video. Put your pencil down. Bouncing a basketball is a great example of the law of conservation of energy. At the top of the bounce, I got a basketball. Let me go grab it. Here it is. Needs to be bumped up, but that's okay. at the top of the bounce, what type of energy does this have? Gravitational potential. Gravitational PE. In fact, it has mgh. What about at the bottom? What type of energy does it have? A half mv squared. Right? I notice, though, if I just drop a ball, it loses height on each bounce. Doesn't that violate the law of conservation of energy? Or does it? Because didn't I say that energy is not created nor destroyed, and so the total amount of energy has to remain constant? Does this violate the law of conservation of energy? Can you hear it? Well, that sound energy had to come from somewhere. It came from the initial potential. And also, where's my basketball players over the years? It generates heat. You've had to warm up basketballs on a Saturday morning when they've been in someone's trunk. How do you warm them up? You pound them really hard against the floor. You're trying to actually transfer some heat into this as well. There is some heat transfer in that collision as well. So we're not violating the law of conservation of energy. If I had the ability to actually measure how much sound energy was given off and how much energy I lost to heat, and also the floor absorbed some of the energy by deforming, if I could measure all of that, I would find that the amount I started with equals the amount that I finished with. So nope. Some energy is lost to sound and heat. And so this brings us to the million-dollar question. If I drop a ball, not throw a ball, if I drop a ball, can it ever bounce higher than it was originally dropped? Sorry? I heard someone. No. Convince me. Why? So if it went higher, it would somehow gain energy from an outside source? So I'm going to say this. No, unless we're clever. And I'll show you an exception. A golfer wants to hit his or her drives further by increasing the kinetic energy of the golf club when they strike the ball, because hitting a golf club is a great example of conservation of energy. You're transferring kinetic energy from the club to the ball. The club slows down, the ball speeds up. What would have a bigger effect, doubling the mass or doubling the club head speed? Why? What's the equation for kinetic energy? Ke equals a half mv what, Rowan? If you double the speed, you'll have 4 times as much energy to give to the golf ball. If you double the mass, you only have twice as much energy to give to the golf ball. So that's why a lot of sports equipment over the past few years has become lighter, not heavier. And I said this before, but it bears repeating if you're an athlete. A lot of the sports equipment is becoming lighter. The trade-off is, you lose a little bit of Ke from the M, but that squared is good. So, doubling the speed. I skipped one example. I'm going to see if you can figure it out in the homework. What's your homework? 1 is good. 2 is good. 3 is good. 4 is good. I'm probably going to give you most of this. 5 is good. 6 is good. Not a big fan of 7. I'll skip 7. 8 is good. We did one like that in the notes. I'll skip 9, but 10 is good. I'll skip 11. 12 is good. I'll skip 13, but I like 14. It's a fair bit of homework, I realize. We're going to be doing, I think, a lab next class, so you won't have a lot of homework next class. So you can lay off some of this if you want to take the gamble until Monday class or Monday evening. But there you go.